Robotics is developing really quickly these days, but we have a big problem: the lack of high-quality real-world data. And for that reason, we need to simulate these robots and simulate the data. And for that, Issac Sim and Issac Lab are probably the best option. This software was created by Nvidia. It's completely free and open source, and you can, for example, simulate robotic arms opening drawers or humanoid robots walking around on a rough terrain. You can simulate a spot from Boston Dynamics. It's all very exciting, but unfortunately not that easy to use. In my previous video, I built a spider bot, a robot with 4 legs, servo mechanisms. It was simulated in Issac Sim and then even learned to walk in Issac Lab. This project was a lot of fun. I asked you, my viewers, if you want to see a longer video about this project, and in the comments, 47% of the comments were just about yes, we want to see a longer video. How do I know that it was 47%? I wrote a custom Python script and I used Gemma 3 LLM to analyze all of the comments, and the result is that 47% of these comments were related to yes, we want to see a longer video. I hope you will enjoy it. I will add chapters to make it easier to navigate. We'll go through how to install Issac Sim, the interface, how to use the examples and built-in assets. I will show you how to export the URDF of your robot from Fusion and bring it to Issac Sim, how to set all the settings and save it as USD, Universal Scene Description file. And then we'll go through Issac Lab, how to install it, how to use it, how to go through examples, how to train the robots that are already built into the Issac Lab, how to run the policies that you train, how to export the policies, and then how to train your custom robot to walk in simulation. But that's not everything, because I also brought this robot in simulation. This is a machine learning robot that I built almost 2 years ago, and it was using LIDAR to navigate through a maze created with cardboard. This time I was able to replicate this thing inside Issac Sim, and with action graphs I created a simple data collection script that was just saving all the data into a CSV file. Then with Python I trained the classifier and brought it back into Issac Sim to test if it worked. It did, and this project is also very cool. I will show you how I did it and I hope you will enjoy it. For the most of it, this video will be just me sitting in front of the computer. It's not going to be as exciting, but if at least 10 people at the end of it will learn something and will install Issac Sim, Issac Lab, will play with their own robots, I will be happy. If you would like to help me a little bit, you can give this video a like, because it really helps to boost a little bit the views and reach more people. If you like content like this about robotics, simulating, building DIY projects, consider subscribing to my channel, because it also helps a lot. Thank you very much. If you have any tips, ideas, please leave them in the comments. I always read the comments, so I would really appreciate it. And before we start with robots, Issac Sim and Issac Lab, here is a quick message from the sponsor of this video. And today's sponsor is Habada and their E3 chair, which has way more features than I can memorize. The chair comes safely packed in a huge box, and assembling it takes literally just a few minutes. Every screw is clearly labeled and the instruction is very straightforward and in multiple languages. After fixing just a few screws, you get a chair that looks like this. Very modern, minimalistic design with plenty of features. All the parts are very durable, and once you assemble the chair, everything feels super solid. And there is just so many features, as you can see, that I will probably miss something in this video. This is the most adjustable chair that I've ever used. With all the supports for your back, it's really comfortable, and you can always find a position that will just simply work for you. You can even lift the whole backrest and put it down, and also perfectly adjust this thing for your head, which is really nice. And of course you can also adjust the headrests, and you can rotate them and even do something like this. And at first I was like, this makes no sense. And then I was like, this is the best thing ever. I work a lot in front of the computer, especially for videos like this one, where there is a lot of programming and a lot of video editing. Taking care of my proper posture and my back during this time is very important. If you are also working a lot in front of the computer, getting yourself a nice chair like this one might really improve the experience. If you are looking for one, I will give you a link to Habada in the video description and their E3 chair, which I can definitely recommend because it's really comfortable. Thank you very much, Habada, for sponsoring this video. Remember that supporting the sponsor of this video means also supporting my channel. And now it's time for Issac Sim. Before installing Issac Sim and Issac Lab, it's a good idea to check if your computer and your hardware is capable of running it smoothly. For that, of course, you have the requirements that look like this for the software, but they also prepared a special compatibility checker that you can just download from the website and check it, which you can do right here for Windows and right here for Linux. The links will be in the description. Just click on the link, you will get a zip archive, you will have to unpack it, and you will get that. In order to run the compatibility checker, you have to just double click omni.issac.sim.compatibility check.bat. And this will open the terminal that looks like this with all the data, but also a small window where you can just check everything. If everything is green, perfect, your setup is great to run Issac Sim and Issac Lab. You can see your current version of the driver, CPU, GPU, RAM, everything else. It works fine, so we can close it and then we can proceed to actually installing the Issac Sim. The way I have it set up on my computer is a double installation of Issac Sim and a single installation of Issac Lab. It's just for convenience, I like using it that way. You don't have to do that, but it's quite easy to use, so I will show you how I did it. First, you have to go to the Issac Sim documentation, and then here in point number 4, you have a link for Windows and Linux. You have to just download the zip archive and extract it all into the Issac Sim folder on the C drive. So that's exactly what I did, and you can see it here. Now, to run this app, you have to run the Issac Sim selector, yeah, exactly this file, isacsim.selector.bat. If you double click it, once again, the terminal will open, and after a while, also a small window where you can just run the app. But to make it even easier, I just created a shortcut to this file and I moved it into the desktop, and then I changed the icon, so now I can just run it as any other app by double clicking. Terminal opens, the window opens, and now I can just click start. It might take a few seconds to run the Issac Sim, that's completely normal, it's just a very big piece of software. So after about 15 seconds for me, the app is running. As you can see, you can move around, you can go through examples. Let's just quickly go through the Issac Sim interface. Here's the main stage, which you can navigate with the right mouse button and moving around. That's how you rotate the camera. To move your camera, you can just use WASD buttons, so it's just like a video game, and you can use Q to move down and E to move up. If you want to add an element, you go to create, for example a mesh, and let's add a cube. So here we have it. If you want to change the light, you can do it here. Let's go with, for example, Gray Studio. This is a bit more visible. If you want to move it, you just use the arrows there. You can rotate it as well with this tool and scale it like this. It's quite easy. You can also do all of the transformations here on the right. And if you want to, for example, change the color, what you do is you go to Create, Materials, Omnisurface, and now we can go to Base and here change the color to whatever you need. If you want to enable the simulation, you click this button on the left. But as you can see, nothing happens because we do not have physics enabled on this cube. So let's add it with this button. Physics, rigid body with collider presets. And now if you enable the simulation, the cube falls indefinitely because we do not have the ground plane. So let's add it. Once again, create physics and ground plane. The ground plane has been added. We can't really see it because everything is white. So let's go back to the stage light. And as you can see, this is the ground plane. So now when you enable it, it will just fall to the ground plane. What is important is that ground plane is visualized like this, but it is actually infinite. So if I just move the, sorry, not the ground plane, but the cube, if I move it, for example, there, you might think that it will fall because the ground plane is not under the cube, but in fact, it won't. The ground plane is just infinitely extended in the environment. You can navigate all of the elements in your scene here on the right. You can hide them, for example. You can move them, you can group them, you can add X-forms and everything else you need. You can also add cameras, you can add graphs, you can add physics elements, you can add robots. But the best part, and probably my favorite part, are the assets that you can find here. Here you can find plenty of robots, like seriously, there's a lot of them. You can find complete environments that are built so that you can train your robots. You can find Issac Lab examples, you can find props, so like pallets, boxes, food, scissors, a lot of stuff that you can use for example, training a robotic arm to grasp things. You can train your robot to navigate in the, I don't know, a warehouse. Let's load the warehouse example because it's very complicated and I like it a lot. And here we have it, complete warehouse with all the shelves, with boxes, with a little bit of a mess inside it, even with a forklift, and with all the details like the lamps, the ceiling, even this stuff on the wall. It's like, it's super detailed, it's super realistic and perfect to train your robots inside here. Now, what if you want to add a robot? You simply go to robots. Let's go with the spot from Boston Dynamics. You just drop it there, and here you have the spot. It really is a lot of fun to create these environments for robotics training, and thanks to all the props that are built in, you can just easily just grab them and put them into your world. It makes it so easy because you don't have to design everything from scratch. But if you go to Window, Examples, and enable Robotics Examples, there is something even cooler because we have like a complete example. Let's go with quadruped one. You have to click it and then click Load right there. And as you will see in a moment, here is the Boston spot. The simulation is already enabled. And now with the arrow keys on my keyboard, I can just walk with the robot. This policy has been trained in Issac Lab. It is already a built-in example, so I have not been training it, and you can just run it like this. And we can do the same with the humanoid one, so let's click it, let's load it, and well, here it is. And as you can see, you can just walk with the robot in the simulation. It has been trained in simulation, and now it works in Issac Sim. But we can also find their industry-related examples. So here is a very popular robotic arm, the UR10, with a pallet, with some shelves, another small warehouse. And now when you load it with this button and then click Start Palletizing, here's how it works. Here comes the box. The robot picks it up and places the box on a pallet. Stuff like this will really change robotics and enable anyone to train very complicated policies and very complicated AI models that will actually take action and execute your instructions that you can, for example, write in a prompt, but instead of just outputting words, it will output action and the robot will execute it. So that's the Issac Sim setup. But now what if you want to also use the Issac Lab? For that, we have to go to the Issac Lab documentation that you can find right here. And I advise you to go with pip installation since it's recommended by Nvidia. You have also other ways to install it described in the documentation. Link is in the description. And here you have to install, you have to activate the Conda environment, and then you have to install everything just line by line, all the libraries. You have to install Issac Sim, and then you have to install Issac Lab. So that's why I mentioned that I have a dual installation of Issac Sim, because I have it set up in the Conda environment, but also just as an app on my computer. That makes it a lot easier to just open the app and play with the examples, you know, set up your OpenUSD files and everything else. And when you want to run the Issac Lab, you just have to activate the Conda environment and run your Python scripts directly from the terminal. The installation process might change completely in the future, so I won't go into the details. If you want to know how to do it, just go to the documentation, it will be linked in the description, and the process will always be up to date. Once you go through all the steps, once everything is ready, you can go down there, and here you will find a section called Train a Robot. And here we can just copy this command. What we can do is go to cd Issac Lab. That's where you have the Issac Lab installed. And now I can do conda activate env Issac Lab. Okay, this is activated, perfect. Now I can paste the script from the website. And what I need to do is change that. We don't need DP. And we need just simply Python. I will also remove the headless tag so that we can see what's going on. And let's run it. If you see that, congratulations, your Issac Lab is installed properly and you can see the robots training. Everything is a bit slow because we have like thousands of robots there and it's all running on a single GPU, which is quite impressive. If you want to run it faster, I will show you how to do that. We just need to stop this training. Let's run it again and add num envis equal to, let's say, 1000 should be fine. And now, as you can see, everything is a little more responsive. We can just smoothly navigate through the world and we can see the robots moving. Now if you let it train for like 20 minutes, maybe an hour, you will see the robots actually start walking properly into the green arrow direction, and also just not dying from touching the floor. But I want to show you just one more example. What if you want to run it faster? Because it runs pretty slow for just 1,000 robots, and usually we want to train for like a lot more than just 1,000 robots. Let's increase it to 5,000 and let's add headless tag. By that, the app won't run the user interface, it will just all run in the terminal, and you will see the progress of training, but you won't see the graphic elements, which make it a lot easier and faster to run. So usually if you want to train your robots, that's how you do it with the headless tag. If you just want to observe it and troubleshoot some problems, obviously you will disable the headless tag to see what's going on with the robots. But once your setup is prepared and everything is working fine, you can run it in the headless mode. It's a lot faster that way. While training, you can see all the information right here, like the rewards, and also the most important part, the mean reward. So this value should be increasing over time as we go through more and more of iterations of our training. And after training for a while, what we can do is run exactly the same command, this time without the headless tag, and let's do it just for 20 robots. What we also need to change is to change the train to play. Now we can run it and we'll see our trained policy running on the robot. So you can easily train with the headless mode. That will like work very quickly. It will train fast, and then you can evaluate your policy and see how it works with the play script just by modifying train to play. It's super easy to do it. And now we are inside Issac lab again, and here we can see the robots walking. Here's one. There is another one on the stairs. And I think there should be some more here in the back. The robot walks without any problems on the flat terrain, on the stairs, on uneven terrain, everywhere. It took maybe half an hour to train this policy. It works on all terrains. This is so cool. Once you are done with Issac Lab, what you have to do is to go to the terminal and press Ctrl+C, and that will close your app. And if you would like to find the policy that you just trained, the files for the policy, you have to go to your Issac Lab folder, then to logs, RSL, RL, because that's what we used for training. The robot was called Animal, and then we have different dates when we trained the model. So let's go to the last one. Here you have different models at different stages of the training. This is the number of iterations that you went through. As you can see, the last one is 1499, but we want to go to the exported folder because once you run the play script, that's where these files will be saved. And here you can see the policy in the Onyx format and the policy.pt file. These are the two files used to run this policy outside of Issac Lab or, for example, in Issac Sim. Before we will export our robot design to URDF, we need a special plugin for that because it is not installed in Fusion by default. So for that you need to search for Fusion to URDF. I will also link it in the description, and you have to open GitHub. The page looks like this one. Here you have to click the green button called code and click on download zip. Under that you can find all the instructions, changes, updates, the lines of code that you have to paste into the terminal in order to install it, and also a short instruction on how to use it, what is important, and how to properly set up your model to properly export it. So let's now open the folder downloads that I have right here, click with the right mouse button and click extract. And now we can open PowerShell. It is very important that on Windows you open the PowerShell and not the traditional terminal, the CMD. And now here you can find for Windows the line of code that we need to copy, and for macOS the line of code that we also have to copy in order to install it. So let's just copy the bottom line and let's go back to the PowerShell window. So here we do cd downloads and now cd again and Fusion to URDF master. So you have to be in this folder, then you can paste the instruction and click enter. And it doesn't work. It looks like we have the Fusion to URDF file master and then again the same folder. So let's do cd Fusion again. And now we can run the previous line of code. And I got an error because this extension already exists in my folders because I installed it previously, but you should see just a success message after running this command. Unfortunately, it's not as easy as just pressing a button and getting a ready URDF from your model. You need to simplify it a bit, and we have to do some additional work. So here is my complete model of the SpiderBot with all the screws, all the details, all the cables of the servo motors, but we don't really need that for simulation, and we don't need that in URDF. So the most important thing is that we also cannot have a nested component. So the way I usually design stuff in Fusion is I have a component called, for example, 3D printed or servos, and here inside it I have all the servo mechanisms so that I can easily just hide them, and the same goes for the 3D printed parts. But the plugin for converting to URDF won't work if you have nested components. So a component inside of a component, you can't have that. So for that, you need to simplify your model quite a lot. It's also a good idea to get rid of any rigid joints that you have inside your model and that you don't need for simulation. So for example, I have a 3D printed part here connected with this 3D printed part with screws and a rigid joint, and I don't need that for simulation. It can be just simply a single part. So for that, you need to use the combine tool and just combine all the parts that are separate into one big part. And actually, to make it even easier, I did that with servo motors as well, and I just simply combined each servo with the arm so that basically I have just 1, 2, 3 parts for each arm, and then this centerpiece together with the servos, with the servo holders, with every single part, it was combined into a single body. I won't bore you with all the details on how I did it. As I said, I just used the combine tool and I got rid of everything that was not necessary for the simulation. That makes it run a lot smoother and a lot faster, and it's also easier to get the Fusion to URDF plugin working properly. So here is the complete version after all the combinations and reducing the complexity. And as you can see, I have basically just arms. So as I said, 3 parts per each arm and this centerpiece that is called base link. And as you can see, when I hide it, everything hides because it's just a simple one single body. And another very important thing is that one of the components must be named base link. So here for me, it is the most central part of the robot that I called base link. It has to be base underscore link, otherwise the plugin won't work. And after all the simplification, as you can see, I have just 3 revolve joints for each arm. Everything else is combined, so I have just in total 3 bodies per each leg, 4 legs and a single base link in the middle, so 13 bodies in total. The way I did it, I kept my complicated version of the SpiderBot as a separate file. Then I clicked save as, and I just saved it as SpiderBot URDF exporter. You can just name it whatever you want and create this simplified version so that whenever you need to adjust your design, you can just go back to this file where everything is, very detailed. And this one will be used only for exporting. It's also a good idea to do this because once you run the URDF exporter, it changes your files a little bit so that in case, you did something wrong or the plugin fails, you have a backup version. So it's a good idea to export to URDF from a separate file. So now if you want to run the plugin, we go to Utilities, Add-ins, Scripts and Add-ins. And here at the bottom, you should find the URDF exporter if your installation was successful. And now we click Play. And here we can just choose where to save it. So let's create a new folder and let's call it SpiderBot URDF video. Okay, choose folder. And after a few seconds, you should see this message, successfully create URDF file. As you can see, we have some old components that have been added. So if you don't want to save these changes, just close it without saving. So now we can go to our folder, SpiderBot URDF video, SpiderBot description, URDF, and here we have all the files. Now, if you want to use it with ROS, you will most likely need all the files. You can find also the meshes, the STL files, and some other stuff that are useful when you are working with ROS. But I'm only interested in the URDF file. The problem is we do not have the URDF file here. But in order to get it to work, all we have to do is change the extension from Xarco to URDF because it's essentially very similar style of file and it should work. So yes, you need to change the extension of this file from Xrcode to URDF in order to get it to work and import it properly into Issac Sim. I really wanted to test my URDF before importing into Issac Sim to make sure that it works and just to have another tool that can check it. Unfortunately, all the online tools that I tried did not work, so I just imported it into Issac Sim with the hope that it will work. It wasn't working a few times when I was working with a more complicated model, but once it was simplified, as I showed you here in my Fusion file, it worked without any problems. If your model is too complex, if there are too many bodies, if you have multiple different joints, it might not work. Also, you have to refer to the instruction on the GitHub page of this URDF plugin. There is all the things explained, what you can and cannot do, so I definitely recommend you checking it out. And now you can open the Issac Sim. I have it located here in the folder called Issac Sim on my C drive. And in order to run it, you have to run the Issac sim.bat script, which I just created the shortcut on my desktop, and I used the icon, and now I can just run it. When you press it, it will run the command line with all the information, but you don't need to worry about that because you also have this small window that opens, and we press the Issac Sim full, we keep everything as default and click start. To import the URDF of our robot, we go to File, Import, and where was it? It was on the desktop in the Spider URDF folder. Here URDF, and here is the URDF. Now here the settings are very important. So the most important part is to choose the movable base here under the links. If you are using, for example, a robot arm that has the static base, which does not move and is stationary, you will choose the static base, but we want the base to be movable. That was one of the mistakes I did when working on the first video, and it took me quite a lot of time to understand that it was a mistake and that was causing all the problems with Issac Sim. And here you can modify all the settings for the joints, like the natural frequency. You can also change it to acceleration. And when you just hold your mouse over that, you have all the additional information that you might need. And we do not have to select anything more. Just click import and click yes. And as you can see, we have our SpiderBot design there. We can also change the lights to see it a bit more. Okay, that might not be perfect, but I think it will work. And now if we go to looks, default material, and we go to albedo, and we can change the color. I don't know, let's go with something like blue, just to make it a bit more visible. Okay, I think that will work. So now, when you press the play button on the left, the SpiderBot will fall because the gravity is enabled, but it will fall indefinitely, as you can see, because there is no ground floor. So for that, you can just create and go to physics and select ground plane. Okay, as you can see, our ground plane is in the middle of the SpiderBot, so let's go a bit down. And now when we press play, the SpiderBot will just simply fall to the floor. But as you can see, the simulation is running, nothing is happening because we don't have any program, we don't have any specified movements. So in order to start like moving our bot, but not really as programming, what we can do is go to Tools, Physics, and select Physics Inspector. This will open a window here on the right that, well, has nothing inside. For it to work, we have to press the refresh button. And that doesn't work still because we also have to select our robots. So in my case, that's SpiderBot. And when you press refresh again, now we can see all the sliders here and also the set limit buttons. And as you can see, I can move the joints and that will move the robot as well because the simulation is enabled and we can see all the changes. You can also stop the simulation and then move the joints of the robot. But as you can see, the physics does not work because the simulation is stopped. So let's turn it on again. And now we can move all the joints and see how it influences our robot movement. If you want to modify the settings of each specific joint, you can just go to the joints and then select the specific joint that you want. And you can go down here and modify, for example, the target position. So basically the same stuff as the physics inspector does, but it's a bit easier to do for all the joints in the physics inspector. You can also modify the dampening, stiffness, target velocity in case you, for example, want to rotate a wheel at a constant speed of your robot. And you can modify all of these settings for each joint, but you can also just select all of them and modify them. As you can see, if the values are mixed, you will see the mixed label right there. And when you are happy with all the settings for the joints, for the robot, and for the world around it, what you have to do is to go to File, click Save As, and that will save your design as a USD, Universal Scene Description file that we will use later in Issac Sim and Issac Lab. So just choose whatever name you want, SpiderBot Tutorial Video, and click Save. And now it's time for the Issac Lab. So let's go to the Issac Lab folder. It's Issac Lab 2, and now we can just create a new project. We have to choose between external and internal one. I will go with the external one. Then the path to the project, let's call it SpiderBot Tutorial. Project name, SpiderBot Tutorial. For my previous video about the SpiderBot, I choose the direct single agent. You can also choose manager-based single agent. And if you want to have multiple robots running different policies in one single environment, you have to go with direct multi-agent. This time I will also go with direct single agent. If you want to know the differences between the direct and manager-based, I will give you a link in the description to an article that explains that. For the reinforcement learning libraries, you have everything explained right there, and also there is this page where you can read more about it, and you can also visit the website for each of these projects. And I will go with the SKRL, but I will also enable RSL-RL. You can select multiple ones with the spacebar and then press enter. And I will also choose both of these algorithms. And that's it. Our project should be created. So let's open the folder and let's go to the C drive. And here we have SpiderBot tutorial, and here are all the files. Let's open the project from my previous video, and as you can see, there's plenty of files, but we are interested only in a couple of them, and mostly in the SpiderBot 3 env configuration and env file. These two Python files define everything that happens inside Issac Lab for the training, and you can find them in the SpiderBot. Well, let me maybe show you how you can find them because it's quite complicated. So this is the SpiderBot tutorial that we just created. So we have to go to Source, SpiderBot tutorial, tasks, directs, SpiderBot tutorial, and here you can find the environment files. What is also very important is that you have to define your own robot for Issac Lab. So how did I do it? I just went to the robots folder, which again, let me show you how to go there. So here is my C drive, here is the Issac Lab folder. I have it called 2, but you can call it just Issac Lab. And then you have to go to the source, Issac Lab assets again, robots. And here you can see the definition for all of the robots inside the Issac Lab. So we have the spot, we have the animal example that I showed you, and we also have the SpiderBot that I just defined. I created a new Python file and I created the definition of the SpiderBot. So let's take a look at, for example, the animal example. Here you can just see how it is defined, and you can modify it. You can also try to ask ChatGPT to modify this for you, provide all the information about your robot. It is usually not 100% accurate because there is not a lot of information about Issac Lab and Issac Sim on the internet. So LLMs struggle a bit to write really good code for Issac Lab and Issac Sim. And here is my definition for the SpiderBot. As you can see, we have all of the joints defined there, all the values. We have the path to our USD file that we just created before with the Issac Sim. And you can just use it. It's also available on the GitHub if you want to use it for my robot or if you want to adjust it for your own robot. In the environment configuration, we configure the environment for the training, all the parameters like the friction, like the mass distribution that you can just modify a little bit to improve how this policy will perform on the different robots. And we can define also our rewards. This is probably the most important part. You will have to play a lot with the reward system in order to just create an efficient way to train your robots. And here is the environment configuration where we configure the policy, the rewards, the observations, and the stop conditions. Because when you run the simulation and when, for example, a part of your robot that shouldn't be touching the floor touches the floor, you have to stop this part of the training because it is not useful anymore and probably something went wrong during training. So you have to define this kind of stop conditions in the getDance function. You also need to define all the rewards, like the orientation, the speeds, accelerations of each joint and everything. And we do that in the getRewards function. And we also have the getObservations functions, and these are the inputs for our policy. I won't go line by line with this code because it would take definitely too much time. Another important thing is the number of iterations, and these values are predefined for skRL and RSL-RL, but I will show you how to modify them. And you have to go to source, spiderbot, tasks, direct spiderbot, agents, and here you can find the RSL-RL PPO, and here you can define the max iterations number as well as all the other parameters. And the same goes for skRL, and here we are using two different algorithms for the training, AMP and PPO. So here you can just go and modify the number of iterations as well as any other values related to training. So that's pretty useful to know. It took me a while to figure out where I can change that. When your code is ready and when you want to run the training for your own robot, what you have to do is do conda activate env Issac lab, as we did in the other example. As you can see, this is activated already. So let's change the directory to the spiderbot3 and spiderbot3 again. Okay, and now what we have to do is do Python source. Was it source? No, it was scripts, I think. Yes, Python scripts RSL-RL train.py. And now we need to provide it the task, and the task name, you can find it in the init.py file. Here is the ID, template spiderbot direct v0. This is the task name, so we just have to copy that, paste it here. Number of environments, let's go with 1000 to make it run smoothly, and we just need two dashes there. And that should run your training. I will run it with the UI mode so we can see what is going on with our robot. If you want to run it faster, as I told you previously, you have to use the headless stack. Let's bring the window here. It takes a couple of seconds to load the 1000 robots, but as you can see, everything's working fine. And we have 1000 spider bots training. And as you can see, every time the part that shouldn't be touching the floor, and that is, let me stop it for a second. So whenever the base, or for example, this part of the robot touches the floor, we just terminate this training example. And as you can see, the robots go totally crazy for now. But with some more training, they will be able to learn to walk. And in the terminal, you can observe the progress of the training. If you want to stop it, just press Ctrl+C. And now if we want to, for example, run the skRL instead of RSLR, what we have to do is just change the path to our file for the training. And that will run the different training methods for our robot. And once you train your policy and you want to test it with Issac Lab, what you do is just limit the number of environments, and you go with RSL-RL and change the train to play. Of course, now I just trained the policy for like half a minute, so it is not going to work because it takes the very last example that you've trained. So this one will be pretty bad, and the robots won't move at all. But let's check it. Yeah, the robots are stationary because the policy is very bad. So yeah, they move a little bit. And if you want to find the files for your policy that you just trained, you go to the spiderbot3 logs RSL-RL. It's cartpole direct because it's the example project. And then you go here and export it, and here you have your policy files. If you didn't run the play script, the exported folder won't exist, so you need to run the play script before actually grabbing these policies from here. And if we go, for example, there, you can also find the policies that have been trained for different number of iterations. So these files are saved during training, and once you run the play script in the exported folder, you can find the policies. If you follow these steps, Issac Lab is very easy to run, especially if you just want to run the built-in examples and play with them, modify them a little bit. If you want to do it for a custom robot, it's a bit harder. It takes time, probably like a few days to configure everything properly and finally run the training as I did for the spiderbot. The problem is, even though I have the trained policy files and I know how to find them, theoretically I know how I should be able to run them just with Python. I wasn't able to grab this policy file and control my robot in Issac sim without the Issac lab. And also I would really like to be able to just run this policy without Issac lab and Issac sim at all, just with Python, with PyTorch, so that I can move it to, for example, Raspberry Pi and easily control my robot. But unfortunately, so far I wasn't able to do that, and I have no idea how to do it. I searched the whole internet, the Discord server for the Issac lab and Issac sim. I asked some people, and it's just very hard to bring it onto the real robot and to skip the Issac lab and Issac sim. Of course, I could learn everything about ROS too and implement ROS on my robot, implement ROS in Issac sim and somehow connect it. There should be a way to do that. Also, there is a way to run these policies outside of Issac sim because people are doing that. I just have no idea how, and I will continue learning and exploring, and I will try to find a way to get it working. At this point, I just don't know how. And I'm really sorry for that. If you know any tips, if you would like to help, contribute, please leave a comment below. You can send me an email. I'm happy to learn how to do it and share it with the community. But how did I do it in my last video that I managed to get the spider bot walking in simulation, and I have been just scripting it manually, all the positions for the servos. I tested it in Issac sim and then moved onto the real robot. That's how I did it. So basically here is my script. It is called spiderbot edit, and all the script does is it loads the spiderbot, the stage, the ground plane, everything that there is, and it also loads motions.txt file. It's just a text file where I hold all the positions and I can manually add more positions if I need to, and every time I save this file it is loaded with Python again and all the joints are moved line by line to proper positions. So now let's open Issac sim. And here is the motion that takes the file. So now if I add another line and let's modify it to something totally crazy. Let's see what will happen if we do it like that. And now I press Ctrl S. As you can see, the robot moves. And that's how we can test all the motions. You can just save it to a TXT file, you can execute it on the robot and see what happens without breaking any servo mechanisms, without breaking any 3D printed parts on your robot. And this is a very simple example that I think can be very useful for a lot of simple robotics projects, because before you even build it, you can test the range of motions, you can see what happens, you can see where's the center of gravity and if the robot is stable. There is just so many useful things that you can do without wasting filament on 3D printed parts that do not work and printing the robotics design that are not yet so polished. You can just test it all in simulation and then go on to the real robot. It's really a lot of fun. But that's not the end, because I have one more idea. I really want to see if I will be able to use Issac sim and create a robot, simulate everything inside Issac sim, generate the data for machine learning, and train a classifier with Python, then go back with this classifier to Issac sim and see if the robot will work as it should. And for this, I will use a very good example, my old project, a machine learning robot that learns to drive in a maze of boxes with a LIDAR data. I think I know how to set it up in Issac sim with action graphs, and I think I should be able to go back with the trained classifier to Issac sim and run this classifier on the robot so that the robot drives autonomously inside the maze. So let's try it. For this example, I will use just all the things that I showed you previously, so we'll go with the flat grid for our ground plane. Then we can import the JetBot from the assets. And if you want to frame your camera perfectly on the JetBot, just select it here, press F. Here we are. As you can see, it's a bit low, so let's bring it up. And I don't need the antennas, so let's select both of them, right click and click deactivate. Now the antennas are not visible. So when I press play, the robot falls. Now I will use action graphs, a visual programming tool inside the Issac sim that you can use to interact with all the objects inside Issac sim. You can of course do all of that in Python, set up your complete scene, but it's a bit easier sometimes in some cases to do it with action graphs. So for that we'll go to Tools, robotics, OmniGraph controllers, and we will choose differential controller. For this kind of robot where you have two wheels on the left and right side, the differential controller is what you want to use. There is also the Ackermann steering, Omni wheels can be used for robots, and then you choose different versions of controllers. But for this one, differential controller is what we want to use. We have to select the robot prim, and that's the JetBot. To check the wheel radius and distance between wheels, we have to go to the left wheel and then choose the collision. And here you will see radius. But something is definitely wrong here because it shows the radius of 50 meters, which is definitely not okay. But I think I went with 0.05, 5 centimeters, and it was fine. Then for the wheel distance between wheels, I will choose the left wheel, and it shows in the Y dimension 0.467. So the other wheel will be minus 0.467. So that will be 0.934, I think. Here we just go with right wheel joint. These are defined right here. And here we have the left wheel joint, and we want to use the WASD keys to control the robot. Press OK, and now when we start the visualization, as you can see, we can control the robot. Easy, nice. But there is a problem. When I press A, the robot turns right, and when I press D, the robot turns left. So we have to fix that, and to fix that you have to open the graphs, press on the differential controller, click right, open graph, and here at the bottom you can see the action graph that was created for us in order to control the robot. So if you want to swap the keys, we just have to find it. This is for forwards, this is for backwards. Here we have A, so we have to change it to D, and here we have D, and we have to change it to A. Stop it, play it. Yeah, and now it works as it should, and you can drive your robot around. Okay, the controlling works fine, but the problem is it's easy to go out of frame. And then you have to reframe your camera view to control the robot again. It's not very easy to do it like this. So let's stop the simulation. Let's begin center on the JetBot. And now I will add a camera. We can't see it, but if we press the eye icon, show by type, and choose cameras, it's very important to put your camera inside the JetBot. So we just have to drag and drop it. Then we can set the position to 0, 0, and also change it as we want. So I will move it a bit to the back. And now we can see a little bit of the Jetson. So let's choose the camera again, and let's move a little bit back. And we can also rotate the camera down a little bit. And now if we go to the camera view again, it works fine. If you press play and start driving the robot, well, the camera is not moving with the robot. Why is that? I know what's the problem. We have the camera inside the JetBot, but it actually has to be inside the chassis. So if we press play now, our camera is moving together with the JetBot, and it makes it a lot easier to control. When you have your camera perfectly where you want it to be, it's a good idea to press the lock icon. That way you cannot move it, and it makes it a lot easier to work with. We can also disable the camera view here. Now we'll add a sensor, and it will be a LIDAR. For that we go to Sensors, Physics LIDAR Rotating. Where was it added? It is right here. Let's move it up so that it's just slightly above the Jetson. We'll go to raw USD properties and we'll enable draw lines. You can also modify all the settings right here. I will modify the minimum range and I will set it to just 10 centimeters. Now when you press play, you can see the LiDAR, and it is visualizing all the lines, which is pretty cool. But it is not detecting any obstacles because, well, there are no obstacles. So let's change it. Create mesh cube. It's a pretty cube. So let's modify it. 0.2, 0.1, 0.2. Okay, 19. And wall. And now when I enable the simulation, as you can see, the LiDAR cannot still see the obstacle. The lines should turn red here in front of the obstacle. It is not happening because we have to add something more to our obstacle, and we have to add the physics rigid body with collider presets. And now as you can see, the obstacle is being detected. We can see the red lines right here, and when we move our robot, the obstacle is still in the same place. You can even just drive into it. I created a complete course for the JetBot with the obstacles. As you can see, it looks just like it looked like for my video that I made almost a year ago about the machine learning robots. Here was the bigger version of this racetrack, and you can easily just modify it by moving all the obstacles. I also added some stuff in the action graph. So most of that, this upper part is actually just the differential controller that was automatically generated for me. I added little notes to know which function does what. Here I modified a little bit the values, and this bottom part takes care of the LiDAR data. Here we take all the points from the LiDAR and we fit that into a custom Python script that I created. Here it is. It was just written with ChatGPT and a lot of my modifications in order to get it to work. You can create a custom script right here by typing script. You can move a node, and here we can easily add the attributes, the inputs, outputs, choose the type of the value, and here you can just write a custom code. So this script, all it does, it takes the LiDAR data and saved it into a CSV file so that we can later process it and train a classifier with that. It's pretty basic and works quite well. So with that script, I was able to just drive the robot around, collect the data, and then I created machine learning scripts in Visual Studio Code with scikit-learn and again with ChatGPT. So all I'm doing is loading the data, clearing it a little bit, and downsampling, because there is a lot of things that we do not need from the LiDAR. We divide it to train, test, split. Then we make sure that our set is balanced. It's very important for machine learning. And then we do feature selection to find the dimensions that are the most important and that are the most correlated with the final outcome, that is the label forward, left, or right. Then I did a simple visualization, which is quite cool because you can see the data from the LiDAR and how the robot is traveling in the maze. And the red points are the selected dimensions. It's pretty simple, but also very cool to see it working like this. And lastly, we have the training and evaluation of our classifier, where we do the classification report, the confusion matrix, and you can see here that it's not the best classifier. I mean, 66% of accuracy is not super high, but it should be enough to make this robot drive in the maze. Oh, and very lastly, I'm just exporting the model to a joblib file. And then I went back to Issac Sim and I created another custom Python script, the node for the action graph that you can see right here. And here I'm just loading the classifier from the file and selecting the features that have been generated. And I'm controlling the robot by just directly plugging the velocity values into the articulation controller and speaking the differential controller setup at all. So it is there, but it is not used. It's just easier to keep it there and connect a few things additionally. And of course, the LiDAR data is passed to the custom node instead of saving it to the file. So after doing all of that, does it work? Well, let's see. Let's enable the simulation. And here goes our robot. And it just drove straight into the wall. That's not good. Let's try again, okay? It usually works. Sometimes it does something completely stupid. But it's really cool to see that, you know, it took me like probably a day to develop all of that. And it completely works, as it did in real life almost 1 year ago when I have been playing with it with the Arduino. Of course, we can also switch the camera from the perspective view to the camera that is attached to the Jetson. And that's how it works. Let's see if it can go the other way around. Play. You can also change the camera from the perspective view to the top one. And default. Oh, it worked quite well on the sharp corner here. What will it do now? That was perfect. Really good job. But of course there is a question. Can I just grab this classifier, put it onto a real robot, and will it work? Will I finally be able to go from simulation to the real thing? let's try it. This is my lucky SpongeBob t-shirt, so I hope the robot will work. I already uploaded the classifier onto the Arduino, the new version that was trained with Issac sim data. The robot is as it is because I kept it after making the video, because it is so cool. Here we have the Arduino board, a small proto board with a few cables, small LiPo battery that is powering the whole robot, and on top of that I have a LIDAR. It's called Delta 2i, something like that. It's no longer produced, I'm still using it on this robot, but I also created a version with a Raspberry Pi LiDAR, something like that. It's a lot more popular, it's also quite inexpensive, and it works on both robots with the same classifiers without any problems. And since this one is already assembled, I will use this robot. And now it's time to build the cardboard racetrack. I fortunately still have the 3D printed holders for the cardboard boxes that I made over a year ago. Very useful if you play with this kind of robots. And I'm running low on boxes because you placed so many orders at industry.cc. Thank you very much for that. If you would like to support my work and buy something from my store, there will be a link in the video description. And now I will use what's left for this robot and later ship your orders with these boxes. The real first test, because I've never tested previously. No. Is it just going forward all the time? It looks like it. It definitely doesn't work. And I don't know why. Let me try to fix it. I'm pretty sure I fixed it. These are the problems of working with simulation and then with the real robot. Everything has to match. And for this LiDAR, the starting point of the measurements are on the right. So that's like the LiDAR would see me right now. But in simulation, it was the front of the LiDAR. So I had to change that in the code, and hopefully it will work now. Let me put the camera on the tripod. Let's start the robot. Let's go. You have to work. Yes. Yes, it was working. Look at that. The real robot in the real world, from simulation to reality. Finally it works. This is so cool. And as you can see, even with all the imperfections, with spaces between the cardboards, it all works because, well, it was very similar in the simulation. I also made the spaces to make sure that the data is just as it is in the real world. This is so cool. Let's try to modify the racetrack. Okay, so what will happen if we put an angle like this right there? Let's do it. Big spaces there. And it does work. But how about when it goes to the other side? Yes, it is working. That was close, but it worked. How about this kind of turn? Barely, but it worked. This is so cool. And as you can see, it is possible to go from simulation and Issac sim to the real world with the real robot that is driving in the real maze. This is so exciting. And of course it had to escape right now when I'm recording. where to find more information about Issac Sim and Issac Lab on Nvidia Omniverse YouTube channel, and especially their live streams, plenty of information there. There is also a YouTube channel called LycheeAI. He seems to be a very nice guy and he also helped me in my own projects. Thank you very much for that. And he makes videos about just Issac Sim and Issac Lab and helps a lot in the community. There is also the Discord channel for Nvidia Omniverse with special channels just for Issac Sim and Issac Lab. You can ask questions there and there's plenty of people willing to help all the time. And lastly, Nvidia has courses on their website. Most of them are free and you can just join and learn everything you can about Issac Sim and Issac Lab. And these courses are still being developed, so in the future I hope there will be some more information, for example running the policies on the real robots. And that's it. I hope you enjoyed it. It was a lot of work to make such a long video. It's the longest video I've ever made. I know it was boring for the most part. Me in front of the computer, nothing exciting, but I hope it will be useful. And you know, if just 10 people after watching this video will install Issac Sim, Issac Lab, will experiment with their own robotics, I will be happy. Please let me know your thoughts in the comments. Remember that I'm not an expert when it comes to Issac Sim and Issac Lab. I just have a lot of fun learning and exploring it and sharing it with you, my community. So if you have any tips, if I did something wrong, please let me know down below in the comments. Thank you very much for watching this video. If you want to see more content like this, subscribe to the channel, like the video. It really helps a lot with reaching more people. So thank you very much and see you in the next one. Bye.